Hey, hi everyone, and welcome again to another lecture video of Maths Unity 4F. So let's get a brief outline of the topics to be discussed in this video and succeeding videos. So let's discuss first the polynomial interpolation. So we will discuss the polynomial interpolation and also the Newton's divided difference. So I will discuss later what does that mean and what is its significance with regards to our nice number. And then for the intended learning outcomes, we want to be able to construct an interpolation curve, which is also curve fitting strategy. And then we want to compare the advantages and disadvantages of Grafton and interpolation. And then we will also solve engineering problems that require interpolation. Okay, so now let's get into it and let's imagine a scenario. So let's imagine a scenario where we have a data of, let's say, a specific uh, fluid, control volume or mass with this varying properties. So let's say you have this fluid or object or mass, whatever, at negative 40 degrees Celsius. It has a density of 1.52 and it has a kinematic, it's really just not kinematic, but dynamic viscosity, and then it has this respective uh, kinematic viscosity. So dynamic viscosity, kinematic viscosity, density, and temperature. So let's say we want to know what is the density at, let's say for example, 30. Okay, so how do we find that? So there are different ways to estimate. No, we cannot really guarantee exactly that we can find out the other properties here as well. So we can try the simplest way of finding this data in between this 20 and 50 degrees Celsius. So the first one that you're already familiar with is linear interpolation. And with linear interpolation, it is usually suffice in handling these scenarios. So you can find what is the density, the dynamic viscosity, and the kinematic viscosity. So we can take this further, and instead of a line, we can imagine a parabola, a cubic function, or a higher polynomial function that represents this distance or this this interpolation in between this 2 points. So if you can remember, again, that interpolation is linear interpolation is just basically drawing a line in between these 2 points. But if we will do, let's say, a quadratic interpolation, it will look like a parabola. So there will be a curving pattern, and it will require, instead of 2 points, we have 3 points. And if it is a cubic, if cubic in nature, you have a cubic polynomial. And instead of just 3 points, we will need four distinct data points. So we are already familiar with this, I believe, because we have already discussed this in your linear algebra. So we can determine the coefficients of our polynomial function, which we will assume, for example, for this example, is p1x squared plus p2x plus p3. So how do we figure this out? We can actually, let's, I can see this. I want to see my notes. So, it's really blurred. Okay. So anyways, what can we do here is we can input the value. So we will want to have these three density values. And then this will be the three density values. And then we have this respective, for example, we just use temperature and density. So we have a function that could take in, for example, it could take in the temperature and it will output the density. So basically, we have a temperature, it will output the density. So our function here, or a function of the density, which is also the temperature, or just change the F into temperature. So T, or the temperature as a function, or actually that's sorry, the independent variable is temperature. I forgot. Sorry. And then we want to find the density as a pressure of temperature, which is equal to some function, which is actually defined. That is this quadratic expression. We have P1, so it's not wrong. So it's P1 x squared plus P2 x plus P3. So what is this, guys? So this is actually not P, but this is called rho, Greek letter rho. So it usually represents the density. So if we have this, we can just correlate this to. So if we input, let's say 300, so we have density of 300. We have to input the value 300 to each of the x here. So we have P1 and then we have 300 squared plus 300 x, sorry, not this one. We have P2 and then 300 and then plus P3, okay, which is also equal to what? So we have this, we have 0.016. So basically, the input is 300 and your output is whatever is this equal to, which is 0.616. So this is your output. So we can create this equation, or we can create more. Since we have a quadratic function, we need 3 points. So this will be the 3 points we have here. Row of 400 is equal to P1 400 squared plus P2 and then 400 and then plus P3 and then equals to 0.525 and then we have row or 500 and then equals to P1 and then 500 squared and then plus P2 and so on. So I hope we get the point here. Now, what is the goal here? So the goal here is actually to find this equation. So to find this equation, we want to just find what are the coefficients here. And to find this coefficient, we can create these three equations with three unknowns. So as you can see here, this will become a system of linear equations. So this will be a system of linear equation wherein our unknowns will be P1, P2, and P3. So it will look like this. We have 300 squared, and then we have 300, and then 1, right? Then we have 400 squared, and then we have 400, and then 1. We have 500 squared, 500, and then 1. And then this is equal to, sorry, I'll just augment this, guys. So we have 0.616 and then 0.525 and then 0.457. So to solve this, we just use the calculator, to make things faster. Let's calculate. So let's calculate this. This will be equal to so moles 5 and 2. So we have 300 squared, 300, 1, and then 0.616. We have 400 squared, 400, and 1, and then 0.525. We have 500 squared, 500, 1.457. So you will have a solution. Well, actually, it is very low. So I will just change the accuracy. So instead of effects, we can just have a, yeah, sorry. Sorry, I need to do this because the coefficient is so low. So we have how many zeros here? We have 5 zeros. So basically, your function here, your row of t is equal to 0.000. So we have 5 zeros. 4515, and then x squared, and then the next value is we have negative 0.01715. So negative 0.001715. And then for the last constant, we have 1.027. So we forgot the x here, but there's an x here, and then the constant is 1.027. So as you can see, you can predict, no? You can predict the value of your density based as a function of t with these three different points. Now, we will discuss this later, but this is usually only applicable. So remember that interpolation is available, it is accurate, or usually accurate if the data that you will input here for x no, is in between, no? In between lang. Yeah. So if it is outside, let's say this range, this 30 to 500, if it is 200, then it might not get this value, or sorry, this 0.746. So it is useful if you want to find, let's say the density at the temperature of 350 degrees Celsius. Okay, so that is polynomial curve fitting. So we can add more data points. So if the data points is n data points, okay, then you will need how many, or what is the degree of your polynomial? The degree will be n minus 1. So what does that mean? So for this example, we have 3 data points. Okay, so the 3 data points, and this would be second degree, which is also quadratic equation, quadratic function. Okay, so this matrix is actually called the van der Monde matrix, and this matrix, this type of matrix is actually very ill-conditioned. So what does that mean? What does the ill-conditioned matrix mean? It basically means that it is very sensitive to changes. And if let's say you have a small round of error, no, then it will largely affect the accuracy of your answer. So that is the definition of an integration-based matrix. Okay, so now it will prevent us, no? So knowing this, it will prevent us from doing higher order polynomials for estimating the what do you call this? The values in between these data points. So we can use only quadratic or even linear interpolations to have some or usually it will suffice for finding the data, sorry, the value in between this data. Okay, so the simplest form of interlinear interpolation is the linear interpolation. So I hope you're already familiar with this. So basically, what does this mean is that the slope basically is equal, okay, around these 2 points. So if you have this first point and you have this second point, then the linear interpolation is basically the point in between these 2 points. So it will just create a line segment connecting these 2 points, and then the estimation of this will be this. So the error of this estimation, so this is the true value, this will be your error. Okay, so as you can see, if you have a curvy graph, linear interpolation will usually have this large error if you are going to calculate. So to simplify this, we have a very simple a simple formula to do this. So if you have to, let's say, define, or you have to find this value in between, which is f1x, then you can use this formula. So more to this later na lang, ano? Okay, so let's begin with this example. So estimate the natural logarithm of 2 using linear interpolation. First, perform the computation by interpolating between ln1 and ln6. Then repeat the procedure but in smaller interval from ln1 to sorry, this is actually not I think I should remove this. Sorry. So from ln1 to ln4, total the true value of ln2 is this. So there is a lot of words here. But if I have to draw this, basically if you have here a graph of the lnx, no? So if you have a curve of lnx, it will look something like this. Something like this. Okay, so this is ln x, no? This is our function ln x, and it will look like this. So basically, we're trying to find or estimate ln2, which is this. This is the exact value. So this is ln2, this is 2, and this is your ln2. But the given here is what? So we have a given ln1. So we know that ln1 is 0. So ln1 is 0. So we have 1 and 0 here. And then for ln, if we continue this graph, we have here ln of 6, which is equal to 1.7918. And then we want to find the interpolation in between these points. So this will be your rough estimation of your linear interpolation. Now we will also do this for ln4. Okay, so this will look something like this. As you can see, the better estimator will be the one closer to ln2. So let's do this. So let's say we want to find first the ln of 2 using ln1 and ln6. So we have ln1 is equal to 0 and ln6 is equal to 1.7918. Okay, so to find this one, what you can do is basically again we have these 2 points. So we have here 1 and 0, and then we have 6 and 1.7918. So what is this, guys? Now, so we have 1 and then 0 and then 6 and then 1.78. So with linear interpolation, you will just connect these two line segments, and then some point here will be an estimate of ln2. So basically, this will be some value of 2, sorry, it's actually 2, and an estimation of ln2. Okay, so how do we do this? We have a general formula, or you can memorize just the rise over run, no? So basically, if you have here the difference of these 2 points, so we have f of 2 minus 0. So we will compare these two first, and then f of 1, which is 0, and then we have here below we have 2 minus 1, and then equals to, we have here a difference between this 1.7981. Okay, 7918, sorry. And then 0, and then we have, so comparing this two, and then we have 1 and 0. Sorry, actually this is 6 and 0. So if we simplify this, we will have a rough approximation of ln2, which is also the function of t. That is, sorry, I will just write this down. So use your calculators to find f of 2. This is equal to 0.3584. Okay, so this will be a rough approximation. So as you can see, it is very far from the exact value. Okay, and then for another alternative way is, instead of ln6 here, so it will be closer. No? So we have here a closer estimate, which is ln4. So basically, again, we have ln1 is equal to 0, ln4 is equal to 1.3863. So if we will visualize this, we have a shorter path, no? So let's say this is your ln4. So you have here 1 and 0. So we have here 4 and ln4, which is equal to 1.3863. So to find the point in between these two lines, we have here, we know that this is 2, but what is this? You can find this using linear interpolation. So again, we have f of 2 minus 0. So basically, we're trying to compare this two. So we have 2 minus 1 for x. And then comparing this two, so we have here for the rise, we have 1.3863 minus 0. And then we have 4 minus 0. Okay, so if you calculate this, so I already have a calculation at the same time. This will be equal to 0.4621 as your estimate. As you can see, this is closer to exact value. So what does this mean? So when you're doing linear interpolation, it is best that you have your data points closer to that value. Okay, so remember that. So exact value. So this is the exact value. So to visualize this, yeah, so this is the visualization again of the linear interpolation. So this is what we did first time, and this is the second time, and this is the true value or the exact value. Okay. So the error from this previous example, as you can see, is this height difference between. No? So again, this is the error for the first estimate. Okay, and this is the error for the second estimate. So we can minimize the estimate by, instead of making a linear interpolation or a line, we can make a parabola or a second order polynomial or a quadratic equation. So we can do the quadratic interpolation. So for simplification, guys, you can actually expand this. If you expand this, it will become a polynomial curve fitting form. But for visualization and for the ease of explanation for later, this is another form for quadratic functions. Okay, so we have here three constants, b1, b2, and b3, to fit into our equation also in some way. So how do we solve this b1, b2, and b3? So to calculate b1, b2, and b3, what we can do is, let's say we let, no? So if we let x is equal to x1, so as you can see now, this will become x1, this will become x1. So if you have x1 minus x1, this will be 0, this will be 0. So we have here the function of x1, okay, is equal to b1. So that's basically it. So we have a formula to find b1. And then let's say we have that x is equal to x2, for example. So if x is equal to x2, this will become x2, this will become x2, this will become x2. So this will become x2 minus x2, so this will be 0 again. So we can cancel this term. So what's left here is this. So we have f of x2 is equal to b1 plus b2, and then we have x2 minus x1. And we know already the value of b1, so we know that this is f of x1, so we can say that f of x2, okay, and then ita-transpose ko na to, no? So I can transpose this to the other side. We have minus f of x1, and then equals to b2, and then x2 minus x1. Okay, and then we can divide this for both sides. We have divided by x2 minus x1. So therefore, b2 is just f of x2 minus f of x1, and then all over x2 minus x1. So this will be your formula for finding b2. Okay, and then for the last one, this is actually a long algebraic manipulation, but I'll save you the time. I'll just show you the formula. So if let's say for example again, if we let x is equal to x3, so if you substitute x3 here, here, and here, this will be f of x3. So even here, no, using this. So f of x3 is equal to b1. So I'll just write f of x1 here. So it's already, we already know b1. So we have f of x1. And then plus, so b2, we already know b2. So this b2. We can substitute b2 here, which is equal to f of x2 minus f of x1. And then all over x2 minus x1. And then we have x3 minus x1. Okay, we substituted x3 here. And then for the last term, we have plus b3. And then we have x3 minus x1. And then we have, sorry, but this is included. We have x3 minus x2. So if we solve for b3 here, actually this is a long, it's a great manipulation. Although I will not show this anymore. We can solve b3 here. This will be equal to f of x2. Sorry, x2 pala. So f of x3 minus f of x2, f of x3 minus x2. And then you have minus f of x2 minus f of x1. And then x2 minus x1. And then over x3 minus x1. So to solve for b3, you have this formula. Okay? So I will explain this later. There is actually an easier way to do this. I will show you the easier method or the shortcut method later for the last example. we already know how to find its coefficients. We can now definitely calculate for the value or the function. So going back again to the estimation of ln2, okay, we now again we want to find ln2. And from the given before, this is the same given before from actually. But instead of a linear interpolation, so to visualize this, brief visualization of this problem is we have here, this is sorry, the graph, and then we have here one, sorry, not this one. This is actually not sorry, this one pala, no? So this is 1 and 0, and then we have here sorry, this one. Somewhere here is we have 4 and 1.3863, and then this will be your 6 and 1.791. Okay, and then we're trying to approximate for ln2 here, which is 2, and the approximation of ln2. So to approximate this ln2, we actually want, or instead of a linear interpolation, it might look something like this. No? So forgive me if this is not exact, but it might look something like this, something like that. So the estimation here will be this value. Okay, so let me show you the calculation here. So for again for a second order polynomial, we have f of x. So we just have a sub 2 here, which basically means this is second order or quadratic. Okay, so we have b1 plus b2, and then x minus x1, and then plus b3. We have x minus x2, sorry, x1, and then x minus x2. Okay, so if we solve for b1, so we're trying to solve for b1, b2, and b3, and then later on substitute the values. So for b1, this will be equal to f of x1. So what is f of x1? So guys, this is the f of x1, f of x2, and f of x3. So basically, you should just have to tabulate this. If it is not implied, so we can just have the tabulation of x and f of x. You have here 0 and 1. You have here 4 and 1.3863. And then you have 6 and 1.7918. Don't worry, I have a shortcut for this one. Let me just get to the basics first. So b1 is equal to f of x1, which is basically this. So we have 1. Okay, that's it. I'm sorry. Sorry, baliktad pala. No? So this is 1 and this is 0. So b1 is actually 0. Okay, so we are done with 0. And then for f of x2, sorry, b2. So b2 is equal to, this is a longer one. We have the difference in between f of x2 and f of x1, and then x2 minus x1, right? So f of x2 minus f of x1 over x2 minus x1, which is basically just 1.3863, and then 0, and then we have x2 is 4, x1 is 1. So this will be equal to, so I'll save you the time, I won't show you the calculator anymore. So 0.4621. So this will be your b2. And then for b3, so b3 is slightly complicated to solve, but this is just we have here f of x3 minus f of x2. Again, there's a shortcut method for this, so don't worry. And then we have minus f of x2 minus f of x1 over x2 minus x1, and then over x3 minus x1. So actually we calculated this, which is equal to this, as you can see. So we're good with this. Okay. So we can just solve for this first term. So f of x3 is 1.7918. And then minus 1.3863. And then for x3 minus x2. So yeah, 4 minus x. Actually 6 minus 4. So 6 minus 4. And then minus, so this is actually equal to 0.4621. We'll already go for this one. And then over x3 minus x1. So x3 here is 6. x1 is 1. So if you solve this using your calculator, I'm going to solve this. This would be equal to negative 0.0518 Okay. So what does this basically mean? So therefore, if we go back to this, your function here, so function is equal to b2 is 0, sorry, b1 is 0, so we have here 0.4621, and then we have here x minus x1, and then we have minus 0.05187, and then we have x minus x1, and then multiplied by x minus x2. So basically, this is your formula to solve for the ln2. So therefore, if you use a calculator, so the approximation of f of 2, if you solve here 2, so it would here 2, 2, 2, okay. So it will look something like this. This should be shown. So we have here so point 0.46 0.4621, and then x here is 2, and then x1 is 1. A minus 0.050187, and then x minus x1, so we have 2 minus 1, 2 minus 1, and then multiplied by x minus x2, so 2 minus x2, which is 4. So you will have an approximation of 0.5658. So you have 0.5658 as your approximation. As you can see, no, so the real value of, or the exact value of ln2 is about 0.63 something, right? 6931. So therefore, yes, 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 yes. Okay. So, sorry. So you have here 0.5658, and you have a difference of 0.6931, which is better than the previous linear estimation. So as you can see, if you use a higher polynomial or higher order polynomial, it will usually most of the time it will be more accurate, but there are cases wherein it might not be accurate. I will discuss that later on at the end of this video. Okay, so we have this interpolation. Now, to visualize this again, so as you can see, the linear interpolation here is slightly off the quadratic interpolation, and it will be closer to the true value. Okay, so that's it. No, and we can generalize this. So we can do cubic, we could do quartic, so on. Wherein this is the general form of the equation. So I'll just skip this one. I will just give you the very easy method to solve this. So for Newton's interpolating polynomial, we have this structure of solving the coefficients. Okay. So basically, just remember this. The entry here will be your first constant. This will be your second constant. This will be your third constant, and this will be your fourth constant. So remember this, okay? As before, and so on. So this will continue for, let's say, finding the 10th order polynomial interpolation of this data point. Okay, sige, let's do this. Okay. So in the previous example, the data points are this, and we want to use again the linear estimate. Sorry, we want to estimate ln2, and we will add another point. So we want to use third order polynomial. Okay, so to avoid confusion, let's tabulate the values, the data points. So we have now 4 data points. So we have x here and f of x. So the first data point is 1 and 0. We have 4 and then 6. I forgot the value, 1.6. just up here to save time, and then 1.7918. So this is from the previous one, and then we will add another data point. We have 5 and 1.6094. So the goal here now is to find the coefficient of a third order Newton's interpolating polynomial. So if this is a third order, we have f3 of x, which is equal to, so p1 plus p2, we have x minus x1 plus p3, then x minus x1, x minus x2, and then plus p4, we have x minus x1, x minus x3. So you can see a pattern here, and then x minus x. So this is multiplied, guys, now. So if this here, there's just no space. Okay, so how do we use the tabulated method? So actually, we can just extend this tabulation if you want, but I'll just write this again. So have here a better representation. So xi and f of xi. So xi here is just basically your x value. So we have 1, 4, 6, 5, and 5. And then f of xi is also the f of x value. So we have 0, 1.863, and then 1.7918, and then 1.6094. Now, to do this, okay, so actually, this is already your B1, okay, and then for the second, sorry, the first divided difference that we call is just to interpolate or do the linear interpolation of this. So how do we do the linear interpolation of this? So we have the difference in f, and then over the difference in, sorry, the difference in y over the difference in x. So difference in f over the difference in x. So to find this first one, we just want to find the difference of 1.3863 and 0. So we have these two rows, guys. So subtract this, and just divide. So we have this, and then divide 4 and 1, 4 minus 1. So we have here 0.4621, 4621, okay? And then do this again. So we will do this again, but we will start here. So it is, we'll start here with 1.7918. So we have two data points, and we will do the linear interpolation again. So we will do the finite difference or the linear interpolation again. So we have 1.79 minus 1.363, and then you have 6 and 4. Okay, so this will be 0.2. I'll just fix this first. No, I'll just fix this to again for decimal places. Okay, so 0.028. So 0.02. Yeah. And then do this again. So we have this data point. So as you can see, this is just a recurring pattern. You have your 1.6094 minus 1.79 all over 5 minus 6. So be careful, no? So if you use 1.6094 as your first term, you will have to use 5 as your first term. Okay? So this will be 0.1824. Okay, so you'll do this again for the second divided difference. Okay, so when do we stop? We stop when there's nothing and or there's nothing or there's no data anymore. Okay, so let's do this again. So what do we do now here? So what we will do here is actually we will start from this row and we will end for this row. So basically your divided difference here, as we call it, will be 0.2028 minus 0.4621, and then all over 6 minus 1. So we have negative 0.0519. And then do this again for this second combination here. But I will just I'll just fix this one again. So we will start with this first row, and then it will cascade into this. Okay, so remember this pattern here. So this will be just the difference of the first and the difference in x. So we have 0.1824 minus 0.208, and then over 550. Okay, so we have negative 0.0204. And then for the last one, okay, we have one last finite difference. So this will be the third one. And usually, if it is the third one, then it is the last one because this is the third order difference interpolating polynomial. So basically, again, we will start with this row. And as you can see, we will now end with the last row here. So we will use this, and then this, and this. So again, the list, sorry, I will calculate this again. Negative 1.04 minus negative 0.0519. So you have to be careful with negative signs. And then what is x? So this will be 5 minus 1. We have negative, okay, sorry, it's 0.0. Okay. So we have 0.007. Okay, so that's the end. So what does this mean now? So basically, again, as I said earlier, this will be your coefficient. So basically, your function, your cubic function or third order function will be d1, so 0. So we will start with this. So we have 0.4621, 4621, and then we have x minus x1, and then minus 0.7519. We have x minus x1, x minus x2, and then last one we have plus 0.0079. We have x minus x1, x minus x2, and then so there's no space anymore, so x minus x2. So you can substitute the values of x1 and x2 here. Okay. So if we input here the value of x1, so x1 here is what? No? So we have 1, 1, 1, x2 is 4. So I won't input this anymore in the calculator at the same time. And x2 is 6. How do we know that? So basically this is 1, this is 2, this is 3, and so on. No? So we have x1, we have x2, we have x2, and x1. So now if you calculate here f3 of 2, so basically if you substitute 2 here, substitute the 2 here in the x, after substituting everything, then you will have a value of where's the value? I don't have the value. Oh, I don't have the value. Okay, we have to do the calculation. So the value here will be so 0.4621. So 2 minus x1 is 1, and then minus 0.00519. And then you have x minus x1, so 2 minus 1 again. And then we have 4 minus 1, 8. Sorry, 2 minus 4 pala. 2 minus 4. Okay, and then plus 0.0079. We have 2 minus 1, then 2 minus 4, then you have 3 minus 6. So the final answer here will be 0.5357. Okay, so your estimate here will be 0.5357. Okay. Let's double check you guys. So this will be your estimate. So as you can see, it is definitely still close to the actual value, which is, so the actual value of 2 is 0.6937. So still close, but usually for highly nonlinear functions, there is sometimes we cannot truly estimate or we cannot get to that exact value. So the cubic estimate here would be this. What is the value for last one? Value is 5.6. Actually, this is lower. Why? It is actually lower. It actually has a higher error. What is that? Ah, okay. I'll just check this later if I have a correction. Sorry guys, I might have a correction. But if it's lower, then you have a caveat here. Yeah, just discuss this. Sorry, I will just put this in the comment if I have an error. Okay, so that's it. And again, the limitation of interpolation is that it is wise to just use the interpolation within the data. You have to interpolate the data. If you will extrapolate using this function, then it will be this, but your actual true curve is this. So it usually doesn't predict outside the data. So usually within the data only, it is only applicable within the data. Okay, and then just an illustrative example of this. So let's say you have a population of the United States from 1920 to 2000 in millions here. So in 1920, you have 106 million. 1930 is 193 million, and so on. And then 2000, you have 221 million. So you can see a trend here that it is increasing, no? In some scale. But if you use a polynomial interpolation here, it will look like this. Okay, so it is kind of good. If you will just find, let's say, what is 1945, what is the population, it will be a good estimate, it seems. But if you try to extrapolate the data, let's say you want to predict what is 2010, okay? As you can see, the curve will be downward and it will be highly erroneous. So use interpolation or interpolation. Okay. So another example of this, or sorry, another caveat of interpolation is that some functions will be let's say that this is highly unconditional functions, no? Or highly nonlinear functions, wherein if the true curve is this, for example, no, this is the true curve, and you find the polynomial function, you will have some oscillations here. Okay, so that is one caveat that you must consider as well. Since as you can see, no, even this is interpolation, it is highly erroneous. No, as you can see, the error is pretty high in some of the regions of this range. Okay, so I think that's it. So thank you guys for this time. I'll just upload the next lecture, which is American. Thank you guys, and bye.